22 for a K3 surface. So that's this bound sort of segues into this definition. We say a K3 surface is supersingular if the Picard rank is 22. So that's as big as possible. That's the biggest number that can occur in any characteristic. So okay, you see a few things from this definition. One, a supersingular K3 surface, this can only happen in positive characteristic. And I guess I should say, for those who maybe have seen these things before, there's a few different definitions of supersingular. This one is maybe the strongest of all the definitions. They're all sort of now known to be equivalent by the Tate conjecture for K3 surfaces, which has been proved. I chose this definition because it's sort of the most elementary to state, but actually everything I'm going to say today works only with the weakest definition of supersingular. I think that's, I guess I hope that these things might have something to say about the equivalence of these definitions.
So what are the other definitions? Will you tell us or not?
Yeah, well, I can just tell you in words. The other definitions, the height of the formal Brouwer group being infinity is the other one I have in mind, which is equivalent to some statement about slopes on crystalline cohomology or various other cohomological statements. Yeah. Okay, so here's an example of a supersingular K3 surface. If E is a supersingular elliptic curve, then the Kummer surface of E cross E is a supersingular K3 surface. So this gives you at least one example for any algebraically closed field of positive characteristic. Here's at least one supersingular K3 surface. Here's another example.
So what's a supersingular elliptic curve?
Yeah, this sort of slightly recursive, but yeah, a supersingular elliptic curve being, I think you can state it in terms of what its p torsion is, or in terms of the number of points if you're defined over a finite field, which I guess you are. Yeah, here's another example. This is a quartic surface in P3. It's always a K3 surface, at least I guess if P is not 2. But if P is congruent to 3 mod 4, this is a supersingular K3 surface. So this is a specific equation for a supersingular K3 that you can write down. I think in general, it's not the question of writing down equations for general supersingular K3 surfaces is quite subtle. So this is one very nice equation, but it's not it's definitely a difficult problem, sort of the general question of writing down equations for these things. Okay, I want to say sort of a few more things about supersingular K3s. There's kind of a nice sort of theory built up around these objects. And I want to just kind of give you like the highlights so you have some kind of picture to have in mind for what these things look like. So let me now assume K is a positive characteristic, and I'll assume P is not 2, but that's probably not absolutely critical. There's actually a 9-dimensional family of supersingular K3 surfaces over K. And I think that's potentially a little bit surprising. The Picard rank is so big, you might think that they were quite limited, but actually there's kind of a large family of them. And here's an important definition regarding supersingular K3s. So this definition is based on a fact, which is that if X is a supersingular K3 surface, then the discriminant of the form on the Picard group has the form minus p to the 2 sigma naught for some integer sigma naught. And this integer is between 1 and 10. And this is what's called the Artin invariant of X. Okay, so this is some number you attach to a K3, and here's what this number looks like in families. Let's say S is a moduli space of supersingular K3s. So for instance, you could take S to be a moduli space of supersingular K3s with a polarization of some fixed degree. Then the Artin invariant defines a stratification on this moduli space. So if you define S sub I to be the locus of K3s whose Artin invariant is less than or equal to some fixed I, then the smallest stratum is S1, which is the locus of K3s with Artin invariant 1. It's contained in S2 and so on. And the dimension of Si is I minus 1. So in particular, S1 has dimension 0. It's discrete. And it's contained in S2, which is one-dimensional, and so on up to S10, which is 9-dimensional. So this is a stratification. Each one is a codimension 1 in the next. And I guess one more fact I'll say, S0 or S1 is 0-dimensional. There's actually, up to isomorphism, a unique supersingular K3 with art invariant 1. And actually, either of the two examples that I wrote on the previous slide are art invariant 1. So they're actually abstractly isomorphic, though that's definitely not obvious. Okay, so that was sort of my little introduction to supersingular K3s. I want to talk for a minute about supersingular twistor spaces. So this is a construction that Max Lieblich and I wrote a paper about. And the new stuff I'm telling you about today is sort of building on that. So I wanted to kind of at least sketch for you how this construction goes. So let's say X is a K3 surface. I'm going to define a functor. I'll call it H2 underline of X comma mu n. And what you do is you sheafify this association. So T, a K-scheme T goes to H2 of X cross T comma mu n. So to be clear here, I'm fixing an n. So n is some fixed integer. It could be the case that P divides n, and actually that's the case that I'm interested in. So I really want this to be a flat cohomology if P divides n. So this is like some kind of higher cohomological degree analog of the Picard scheme, but with mu n replacing gm. And so here's a fact about this functor. It's representable. So it's some group scheme over K. Okay. And let me let U be the connected component of the identity. So this is some connected group scheme over K. And here I've switched out P for N. So now I'm specializing to N equals P. And here's a fact. X being supersingular is actually equivalent to U being positive dimensional. I mean, among K3s is equivalent to U being positive dimensional. And actually, in this case, U has to be A1. So this is, you could take this as a definition of supersingular, for instance. Okay.
Can I ask if X is not a K3, is this still representable or not, the functor?
Yeah, that's a good question. It actually is. I think Martin Olson and I have proved this, but I think that's in like that's something we've sort of recently worked out. Yeah, so I guess to be clear, when I say U is isomorphic to A1, I mean that as a group, U is isomorphic to GA, the additive group, and so its underlying scheme is A1. Okay, so combining this U is isomorphic to A1 statement with this representability, here's what you get. You get that there's a universal class in H2 of X cross A1 comma mu P. Or you could take its Brouwer class, A tilde, in the Brouwer group of X cross A1. And this class is, in particular, it's non-isotrivial. So it's not pulled back from X under this projection. It's sort of genuinely varying over A1. All right, so this is the starting point for the twistor construction. What you do is you take a primitive Mukai vector in the extended Nurens-Vary group of X. Let me define this thing. So I'm calling it mathfrak X of V, and then I have it not up there. And this is the moduli space, the relative moduli space of alpha twisted sheaves on X cross A1 over A1 with Mukai vector V. So there's some implicit polarization here that I want to take to be sufficiently generic. So this is a family of varieties over A1. And I want to assume that we're in some nice situation. So we've picked V and we've picked the polarization so that this is a family of symplectic varieties over A1. So for instance, if V squared was equal to 2, or wait, is that a, I think that should be a plus there. Yeah, that should be a plus. for instance, this could be a family of K3 surfaces over A1. So this is the twistor construction. It's a family of varieties over A1 that arises in this way by taking a moduli space on this sort of twisted sheaves where the twisting is this universal Brouwer class. So I guess one thing to point out, these families are frequently non-isotrivial. So even though sort of the family of varieties that you're taking a moduli space on is just the trivial family, it's X cross A1 over A1, the Brouwer class is non-trivial. So you do actually, at the end of the day, this does spit out a sort of genuinely interesting family of varieties. And it's going to depend on B. For some choices of B, it might not, but for many choices of B, it does. So what Max and I did was we took these families, and we sort of thought about them and thought about like what how many of them you get. It turns out you get quite a lot of them. They kind of cover the moduli space, and you can do some things with them. So let me keep going. Here's kind of a key result about supersingular K3s. Rudikov and Shafarevich proved that they do not degenerate. So, for instance, what this means, if V squared is 0, if you have a twistor family and it's a family of K3 surfaces, that they will be supersingular K3 surfaces. By this result of Rudikov and Shafarevich, you can show that this family actually extends to a family of K3 surfaces over P1. And I mean like a legitimate, it's a smooth, proper family of K3 surfaces over P1. So I guess I should point out, this is a very special fact about supersingular K3s that you can have sort of interesting families over P1. But here's the goal. I want to find a geometric construction which produces families over P1, which compactify the supersingular twistor spaces. So just to be clear, what's the obstacle here? The obstacle is that this Brouwer class does not extend to a class in the Brouwer group of X cross P1. So the situation is we have this sort of geometric construction, which is pretty canonical. You start with a K3 surface X, and you find this universal Brouwer class, and then given a choice of Mukai vector, you produce a family of K3 surfaces or of higher dimensional symplectic varieties over A1. And so you just kind of spit out a bunch of families like this. And then we know sort of abstractly for various reasons that these families actually extend to families over P1. So I think it's a natural problem to try to find some extension of this construction or some way of rephrasing this construction that actually spits out the full family over P1 in sort of one shot. All right, so here's a clue as to what could be going on with this family. And I found this clue rather intriguing. There's a Torelli theorem for supersingular K3 surfaces, which is phrased using crystalline cohomology proved by Ogus. And one thing you can do, if you take one of these twistor families, you can study in the period domain, you can find what the period of the point at infinity would have to be. So at least in the case when B squared is equal to 0, you can check that whatever surface that fills in your family at infinity is, it actually has to be the inverse Frobenius twist of the fiber over 0. And I find that kind of, the inverse Frobenius twist over K. And I don't know, I found that kind of intriguing, in particular that says to me that something somewhat non-trivial has to be going on. Like there has to be something kind of interesting going on in infinity to be able to produce this inverse Frobenius twist. All right, so I'm going to tell you today about what some recent work of mine, which I think solves this problem in some cases. And so the sort of starting point for this is to rephrase what it means, rephrase what a twisted sheaf is for a Brouwer class whose order is P, where P is the characteristic of K. So the starting point for this is Cartier descent. Cartier's inseparable descent. So I just wanted to kind of recap this. This is sort of like a fundamental sort of object or something in positive characteristic. So let me say X is a smooth K scheme and E is a coherent sheaf on X. If you have an integrable connection on E, there's some section of end E tensor omega 1 attached to this connection, which is called the P curvature. This is sort of like, this is a new thing you can define in positive characteristic. And here's the observation. If you have a coherent sheaf on X and you pull it back by the Frobenius, so you do Fx upper star of E, this is equipped with a canonical connection, and this connection is integrable and has P curvature 0. So here's the definition of the connection. I wrote it down here. You take S tensor F to S tensor 1 tensor dF. And you can note that actually, given this, the Frobenius pullback with this connection, you can recover the original sheaf E by taking a set of horizontal sections. So if you're just looking at this formula, why is this reasonable? Well, how could it be the case that that S tensor F gets sent to 0 by this connection? Well, if F was a pth power, then dF is 0. And I guess the statement that this is equal to E is saying somehow that like that's the only way you can get 0. All right, so this is Cartier's theorem, that these two functors that I've just described actually give you an equivalence of categories between coherent sheaves on X and coherent sheaves on X with an integrable connection with P curvature 0. And there are two functors in both directions. Starting with the coherent sheaf on X, you can form the Frobenius pullback and equip it with the canonical connection. And vice versa, given a pair E comma nabla, you can take the set of horizontal sections. Okay. So this is more or less like faithfully flat descent, but now where the flat cover is the Frobenius morphism. It just turns out you can phrase this descent datum in this sort of differential geometric way. All right, so what I want to explain is a version of this for twisted sheaves. And I think that a good way to sort of come at this is from thinking about general foliations. So in this context, I'm going to say that a foliation is a subbundle of the tangent bundle, which is closed under Lie brackets and pth powers. So this is like a sub-restricted Lie algebra of the tangent bundle. Here's another notion. A morphism from X to some other scheme Y has height 1 if you can find a map from Y to X such that you have a diagram like this, so that this map from X to Y kind of factors the Frobenius. So if you're thinking about what such a thing would look like in coordinates or something, pi would be like, the Frobenius is like raising all the variables to the pth powers. Pi might be like raising only some of the variables to the pth powers. And then the map from Y to X would be raising the rest of them. And these two objects are actually tightly related. If you have a flat height 1 morphism, then you can take the relative tangent bundle of the morphism, and that gives you a foliation. And actually, this gives you a 1-to-1 correspondence between foliations and height 1 morphisms. So the functor in the opposite direction, given a foliation, you can take the subsheaf of OX, which consists of sections that are annihilated by the foliation. And that defines what Y is. Okay. And this equivalence actually tells you what this equivalence gives you or leads to an equivalence at the level of sheaves. There's an equivalence of categories between coherent sheaves on Y and coherent sheaves on X for a certain sheaf of non-commutative algebras. So here U of L is the restricted enveloping algebra, the restricted universal enveloping algebra of L. So this equivalence, co-Y is coherent sheaves on Y. If you pull back a coherent sheaf on Y, you get a coherent sheaf on X. And this coherent sheaf is canonically equipped with the structure of a module over this enveloping algebra. So as a special case, this recovers Cartier's theorem because you could take pi to be the Frobenius of X. So this map from Y to X is the identity. The foliation this corresponds to is the entire tangent bundle, Tx. And a module for this universal enveloping algebra of Tx is actually just a coherent sheaf with an integrable connection with P curvature 0. Okay, so this is like a generalization of Cartier's theorem.
So L in there was the foliation?
Oh yeah, yeah. L is what I called F earlier. Thanks, Arnd. Yeah. I switched from L to F, or from F to L. So let me go back to the motivating problem. Let's say alpha is a Brouwer class on X. The Frobenius pullback of a Brouwer class is P times the Brouwer class, and this is just because if you think about how the Frobenius acts on sections of GM, it's multiplication, it's raising to the Pth powers. So let's suppose your Brouwer class is killed by P, which is the case in the situation we were thinking about earlier. Geometrically, you could think of this alpha as corresponding to a mu P gerb over X. And the fact that this class is killed by P tells you that there's a map pi that makes a commutative diagram like this. I don't know, I find it help. You could also think of this as being if curly X is sitting over X and you do the Frobenius pullback, then the Frobenius pullback has a section. So that's the map pi. And actually there's a canonical choice of pi, which is maybe not extremely important, but I think is interesting. So anyway, the point of this is that this looks kind of like a foliation. This looks like a height 1 morphism, but now curly X, instead of having a scheme Y, you have a stack curly X. So I think this is one way to motivate the problem, which is we want to find a stacky analog of a foliation. So we want to find, if this is a height 1 morphism, but now we have a stack instead of a scheme, we should try to find a corresponding notion for foliations. Okay. So you can do this, and I think this is kind of a nice, I think the result is kind of pleasant. I think it's not like completely new. It's maybe like a sort of rephrasing of sort of old results of Ekadal, and maybe you can find parts of this even in SGA. But I think it's kind of this is at least the perspective that speaks to me. So I just want to tell you what the output of this is in the special case where the stack is a mu P gerb, which is sort of the case we care about. So the starting point for this is something that you can find in the literature called Picard algebroids. You can find these in the sort of, they seem to be used a lot in the differential geometric literature. I learned about them from Beilinson and Bernstein. And it's kind of a fun little sort of gadget. So let me tell you what it is. A Lie algebroid on X is a Lie algebra, so a sheaf of Lie algebras, L, equipped with a map alpha, which is called the anchor map, and it satisfies this condition here. So here, X and Y are sections of L, and F is a section of OX. So a specific case of this, if you have a sub bundle of the tangent bundle, that will satisfy this condition. A Picard algebroid is a short exact sequence like this. So OX goes to L goes to TX. Here we require that alpha is a Lie algebroid, and we regard OX as a Lie algebra by giving it the trivial bracket. So the Lie bracket on OX is trivial. Another way of saying this is that a Picard algebroid is a Lie algebroid such that alpha is surjective, and you also have a distinguished global section of L that's nowhere vanishing, and it's central. All right, so what I want to do is find the right restricted analog of this. So I want to equip all of these Lie algebras with a restricted structure, and here's what you get if you think about that. I'm going to say that a restricted Lie algebroid is basically a Lie algebroid where L is now a restricted Lie algebra. And it turns out the right thing to do is to equip alpha, to demand that alpha satisfies this identity here. So this actually, I first saw this in a paper of Langer. Okay, so this is a restricted Lie algebroid, and now I want to also stick on the word Picard. So next up is a restricted Picard algebroid. So this is a short exact sequence like this. Now they're all restricted Lie algebras, and what restricted Lie algebra structure do we give OX? Well, it's going to have the trivial bracket, and the restricted structure is 1 goes to 1. So the Pth power of 1 is 1. Okay, so that's the definition I want to look at.
You can ask, what does restricted mean? Did you tell us, Lord? Restricted, what does this
No,
mean?
no, I didn't tell you. Yeah, so that's a good question. So a restricted Lie algebra is a Lie algebra equipped with an operation, which is denoted parentheses upper bracket P, which goes from L to itself. And this operation has to satisfy a list of slightly complicated looking identities. And the key example is the tangent bundle. The Lie structure on the tangent bundle is the bracket, and the restricted structure on the tangent bundle is you send a derivation d to the p, the pth iterate of the derivation, which is again a derivation because you're in characteristic p. So here's something you can do with these things. You can classify Picard algebroids and restricted Picard algebroids in terms of cohomology. So this is Beilinson and Bernstein did Picard algebroids, and what they showed is that they're canonically sort of classified by this cohomology group. So this is a truncated de Rham complex, and it classifies isomorphism classes of Picard algebroids. So just to orient yourself, why is this reasonable? Well, there's a natural map from this cohomology group to H1 of omega 1. And if you take the image of the class that classifies L under this map, you get the underlying extension of OX modules of L. So a Picard algebroid is in particular an extension of TX by OX. So it has a class in H1 of omega 1. And this is how it arises in this. So sort of like the fact that you can lift this class to this slightly larger cohomology group, H1 of this truncated de Rham complex, this is sort of, that comes from like the extra Lie algebra structure that you have. Okay, so you can work out a similar classification for restricted Picard algebroids, and you get this cohomology group here. So here, Z omega 1 is it's closed one forms, and C is the Cartier operator. And just to sort of orient ourselves again, there's a natural map like this, and this is forgetting the restricted structure. So what this map does, the level of algebroids. Okay, let me return to the motivating question, which was say something about mu p gerbs in terms of restricted Lie algebras. Attached to a mu p gerb, there's actually a canonically associated restricted Lie algebroid. So I wrote it down right here. Here, T bullet is the tangent complex. Let me just tell you the result. The result is that there's a canonical equivalence between mu p gerbs and restricted Picard algebroids. And I think it's really instructive to think about cohomology groups. So at the level of cohomology, this is reflecting the fact that there's a canonical isomorphism like this. So on the left-hand side, we have flat cohomology of mu p, and on the right-hand side, it's cohomology of this complex. So I want to think about this as being like, you have this flat cohomology group, and it's classifying it in terms of some kind of de Rham object. Now it's a de Rham complex with the Cartier operator mixed in, which is like a little bit more complicated. Okay, so that's sort of the background. Now here's the cool thing. How does this help us with sheaves? Well, a restricted Picard algebroid, there's a natural notion of a universal enveloping algebra. And this equivalence comes with, or sort of plays with, an equivalence of categories between alpha twisted sheaves on X and modules for this restricted universal enveloping algebra. So I just want to like take a step back for a second. What this is saying is that if alpha is a Brouwer class on a variety of characteristic P, and alpha is killed by P, then alpha twisted sheaves are the same thing as sort of coherent sheaves on X equipped with a structure of a module over this is like a non-commutative ring on X. And it has some kind of differential geometric flavor. So such a module is something like a coherent sheaf with connection. And this is really special to this situation. This is, I don't think anything like this is true outside of this. So you need a Brouwer class in characteristic P, and you need P to kill the Brouwer class. So I want to highlight a special case, which I think is interesting. There's a special case where you can actually unpack this in terms that you don't need this the algebroids or anything like that. So let's say X is a supersingular K3. by what I sort of said earlier, there's a natural way of thinking of H2 of x mu p inside of the de Rham cohomology. So this is some subgroup. It's as a group, it's isomorphic to the additive group of K, but it's usually going to be a nonlinear subgroup. It's not going to be like a subvector space. There's another subgroup inside the de Rham cohomology, which is F2H, that's also isomorphic to K. This is the second piece of the Hodge filtration. It's the group of symplectic forms on X. Here's a fact that I still find really cool. If the Artin invariant is 1, then these two subgroups are equal. So if the Artin invariant is 1, there's actually, given any of these classes in H2 of X mu P, there is a canonically associated symplectic form on X and vice versa. And this actually has a pretty strong consequence in terms of this, equivalence with twisted sheaves that I put up earlier. Here's what you get if you unpack all these things. So let's say the Artin invariant is 1. If you have a class alpha and you take the corresponding symplectic form, then alpha twisted sheaves on X are actually the same thing as pairs E comma nabla, where E is a coherent sheaf on X and nabla is a connection on E. And now the conditions I'm putting in nabla are that its curvature is equal to sigma. So its curvature is this symplectic form. And then you also have some condition on P curvature vanishing. So this is a consequence of the previous equivalence that I put up. It turns out that when you sort of unpack what it means to be a module over this universal enveloping algebra, in this case, this is what pops out. So at least, I mean, Artin invariant 1 is certainly extremely limiting. There's up to isomorphism only one such surface, but at least my experience has been that if you can understand this case, then you can probably understand the general case. And I also think this is cool because it's sort of making contact with the sort of symplectic nature of a K3 surface. All right. So this was sort of the starting point, but you might reasonably ask, like, what did you gain by doing this? This was all kind of somewhat formal equivalences. In other words, you might ask, how was it helpful to rephrase twisted sheaves in terms of modules over such and such non-commutative ring? Well, it turns out there's one more sort of move you can do when you're working with modules over these filtered rings. And that move is, it appears in lots of settings. It's sort of a variant of the Reese construction. Sometimes it's called like quantization or Simpson's mixed twistor construction. And let me tell you what it spits out in this case. Let me call V V is the scheme associated to this vector space F1H. Okay. There's a universal Picard algebroid on X cross V over V. Hopefully that's plausible. This is the cohomology group that classifies Picard algebroids. And there's turns out to be a universal one on this whole thing. And let me let D be its universal enveloping algebra. So D is a sheaf of filtered algebras on X cross V. And this is, Bailenstein and Bernstein call this a sheaf of twisted differential operators. Simpson calls this, I think, an almost polynomial differential operators. Let P be the projectivization of this piece of the Hodge filtration. It turns out this sheaf actually extends to a sheaf on all of X cross P. And I'll call it D bar. So this sheaf D bar, let me just tell you a few of its properties. One, when you restrict it to this big open set, you just get back D. And if you restrict it to the hyperplane at infinity, it's a commutative algebra. Okay. So I'll say more about the specifics of this in a second, but the point of this is that somehow there's a natural way of compactifying such a filtered algebra, which wasn't the case when you were just thinking about twisted sheaves or Brouwer classes. So here's some words that these are all sort of variants of these ideas. So let me return to the setting of a supersingular K3. We have this curve U, which I'm still thinking of it sitting inside the de Rham cohomology. I can take its projective closure. So this curve U, you can really just like, you can write down an equation for it in the Drom cohomology. It's something you can think about very concretely. And what you can see if you write down this equation is that it's a rational curve. It's either smooth if the Artin invariant is 1, or it has one cusp at infinity if the Artin invariant is bigger. So its normalization is P1. I'm going to write this P1 as P1 sub TW, because this is, I'm going to think of it as, this is what I'm going to call like the twistor line. So it is just P1, but I think it's helpful so it doesn't get confused with other P1s in the future to give it a special name. So this contains U as an open set, and the complement of this open set is infinity. All right, and U is abstractly isomorphic to A1. I think it's helpful to just give it a different name too. All right, so here's the result of all these constructions. So if you have a supersingular K3 surface, then there's some sort of canonically associated sheaf of associative non-commutative algebras dTW on X cross P1 over P1. And here's some of its properties. If you take a lambda in P1 and you look at the fiber of dTW over lambda, and you take the category of coherent sheaves for that algebra, if lambda is not infinity, you just get alpha twisted sheaves for the class alpha corresponding to this lambda. And this point at infinity that you've added, if you do the same thing there, it turns out what you get is just p nilpotent Higgs sheaves on X. So here, a Higgs sheaf is a pair E comma phi, where E is a sheaf on X and phi is a map from E to E tensor omega 1 of OX modules. And it satisfies some condition. Okay, so this is sort of the output of all this stuff. There is sort of a natural category of sheaves that compactifies these categories of twisted sheaves. And it turns out what it is the category of p nilpotent Higgs sheaves. Right. And such things have been studied sort of in enough generality by some people that we know that there's a good theory of sort of moduli of semi-stable modules over this thing. So we're now in a situation where we can just take the moduli space of dTW modules that are semi-stable with some fixed Chern characters or something, and this gives you some object compactifying the supersingular twistor spaces.
And is it still a K3 category everywhere?
No, this category at infinity is much less well behaved. Yeah, it's going to be. Yeah, I think not. I think the answer is no.
I mean, do you get a symplectic variety as a moduli space still?
Well, yeah. So you have to work a little bit. So let me say something about that soon. So let me just unpack this in this special case because I think this is kind of fun. If the Artin invariant is 1.
So can I also ask a question about this definition you just made?
Yeah.
In the analogy with with complex K3 surfaces and usual twistor lines, is there a way to think about this thing that you just introduced?
It's not clear to me what if there is like a sort of direct analog. Yeah.
Okay.
Yeah, I think the answer is it's not clear to me. Yeah.
Cool. Thanks.
So in the case of Artin invariant 1, you can sort of interpret these things a little bit more concretely. So I just want to write that out. So let me say a T connection it's sort of like a connection, but it satisfies this identity where you twist it by T. So one way to get a T connection is to multiply a usual connection by T. So if the Artin invariant is 1, then this twistor line is the projectivization of F2H, as I said before. And here's what you get if you sort of unravel all this stuff. This category of modules over dTW is at a point with homogeneous coordinates sigma t is what I wrote on the right-hand side. So now you have a T connection and the curvature satisfies this identity here. So I think you can see from this how it's sort of scaling. If you let sigma go to infinity, what you end up getting at infinity is basically is 0 connections, which are the same thing as Higgs sheaves. So let me now talk about these twistor spaces. So let's sort of run through the construction again. So let's say you take a primitive Mukai vector. You form this relative moduli space that I talked about earlier. And let's say we're in some nice situation. So we picked V appropriately and we picked the polarization appropriately so that we get a family of smooth varieties. I'm going to define W. This is another Mukai vector to be this. Why am I picking this one? Well, this is the Mukai vector that the Frobenius pullback of a sheaf with Mukai vector V has. So this is something you can just compute. Okay, so now let me let M be just the moduli space of DTW modules on X cross P1 over P1. Okay, so this M that I've classified, if you restrict back to A1, so you restrict to the complement of infinity, you just get back X of V naught. Remember, the equivalence between these two is if you take a sheaf, if you take an alpha twisted sheaf on a fiber, then you do the Frobenius pullback, and that Frobenius pullback is equipped with some canonical module structure over D. So that's why you have, on one side you have V and on the other side you have W. All right, so this, we wanted to compactify. This M thing is a proper, it's a proper scheme over P1, but the fiber at infinity is going to be kind of poorly behaved in general. For instance, you can compute the expected dimension of this moduli space. Like it's a moduli space of Higgs bundles. In particular, a usual sheaf can be considered as a Higgs bundle where you just take the Higgs field to be 0. And if you think about what the expected dimensions are, the expected dimension of the fiber at infinity is going to be much larger than the dimension of the other fibers. So if you want to get a reasonable space out, like at the bare minimum, what you should do is the following. You should take the closure of XV naught in M. That at least gives you a space that has the right dimension on all the fibers. And then maybe it's not even normal, so you should probably normalize. So this is like the bare minimum you should do if you're trying to get a nice family of varieties out of this. So here's my question. When is this procedure that I've just talked about, when does it spit out a smooth family of varieties? Or more generally, the question is what's going on at infinity? So I guess I've sort of outlined some involved construction, but the point of it is that at the end of the day, it spits out a canonical proper variety, proper family, compactifying the supersingular twistor spaces, and we want to sort of understand this family. All right, so in the last 15 minutes, I want to tell you about what I've done to try to answer this question. And I think the answer to this question, I think it turned out to be, at least in my opinion, a little bit interesting. Like for instance, I think that these compactifications turn out to be kind of nicely behaved, and they're smooth. They're smooth reasonably often, which I still find kind of surprising. Okay, so let me tell you about the case. There's sort of one case where I think I have a reasonably complete understanding of what's going on. And there's tons of cases where I don't know what's going on. But let me tell you about the one case where I think I know sort of what's going on. And that's the rank 0 case. So let's say that C is a smooth proper curve of genus greater than or equal to 1 in X. And I'm going to assume that the class of C in the Picard group is primitive. And let me let curly C be the universal curve. So here's the result. I'm going to take the Mukai vector to be 0, C, S. So S is some integer. And then here's the extra condition. If the Kodaira-Spencer map of C to G is generically injective, then this thing actually is a smooth family of symplectic varieties. So you have this extra condition, which I'll say more about that in a second. I think I guess I should say, I think the theorem, I think this is essentially the optimal condition or at least I would expect it to be more or less optimal. And I guess to be more precise, what's going on is, well, okay, I'll sit in a second. So let me say a few more words about what's going on with these families. So there's, I guess I'll do two things. One, I want to describe to you a little bit more some kind of geometry of what's going on with these families at infinity that goes into proving this. And then I want to discuss some parts of the proof. Okay, so there's something called the support morphism, defined I think by Portier, and attached to a sheaf E of the sort parameterized by these moduli spaces is something called the fitting support. And in this context, this gives you a morphism from X of E now to OPC. So remember the sheaves that are parameterized by mathfrak X, they're sheaves they're the Frobenius pullbacks of sort of line bundles on the fibers, or line bundles supported on curves in the linear system C. But actually this map factors through a PG sitting inside here. And okay, there's a lot of potentially very confusing things going on here, at least confusing to me, having to do with various Frobenius pullbacks and various settings. But the output of this is that this family, this curly XV that I talked about, it's equipped with a map to PG. So this shouldn't be surprising. Away from infinity, this family is just isomorphic to a moduli space of twisted sheaves on X with some Brouwer class. So each one of those has a map to PG just by taking the fitting support. And I mean, the varieties away from infinity are isomorphic to those varieties, so they also have a map to PG. And then just because of how we produce this compactified family, there's also a map at infinity to PG. So I want to think of this family as being, this XV it's a family of varieties parameterized by P1, and each member of this family is equipped with a map to PG. So what can we say about these morphisms? So for each lambda in P1, you can take the fiber and you get some variety that has a map to PG. So here's my description of these morphisms. Let's suppose we're in a situation, so we're still in the situation 2 slides ago. In addition, I'm going to assume that this family is not isotrivial. So this is a condition on V. If lambda is not infinity, then this map is a Lagrangian fibration, which is actually an Attal form of the fiber over 0. Okay, so it's a this XV lambda is it's a holomorphic, it's an algebraic symplectic variety of dimension 2G, and this thing is a Lagrangian fibration. What's going on at infinity? Well, actually, the fiber at infinity is not a Lagrangian fibration, and let me tell you why not. First of all, this is supposed to be a birational correspondence between the fiber at 0 and the Frobenius twist of the fiber at infinity. And it's actually an isomorphism if the Kodaira-Spencer map is injective. Okay, so this is something you can produce. And under this birational correspondence, you can say something about what F infinity is. And here's what it is. The map to PG, F infinity, I guess here I have the Frobenius twist, that's not too important, is not Stein. Its Stein factorization is the Frobenius of PG. So what the picture is, you have this family of varieties that have a map to PG. Away from infinity, this map is it's a fibration. It is Stein. At infinity, something weird happens, and this map all of a sudden is now not Stein. It factors through the Frobenius of the base. So this is like a there's some kind of like interesting thing going on with this fibration at infinity.
What do you mean by Stein connected fibers, or what?
I mean that the push rod of O is O.
Ah, okay.
Yeah, so the fibers are all connected, even over infinity. It just happens that over infinity, the fibers are all in one reduced because you factor through the Frobenius. Yes, this is sort of a special thing, a special positive characteristic thing. At the level of Picard groups, if you look at the pullback of O1 on PG, what's going on is that the class of O1 at infinity is now divisible by P in the Picard group. So this is, it's a primitive class everywhere except at infinity, all of a sudden becomes divisible by P. Okay. And let me say, let me now suppose the genus is 1, so we're just an elliptic fibration. So C is a smooth fiber of some elliptic fibration on X. I want to say, I can say pretty precisely what's happening in these different cases. So the Kodaira-Spencer, oh, okay, that's, there's 2 different G's now. The Kodaira-Spencer map, it's a map from the tangent bundle of P1, or really of an open subset of P1 to something else. So either the Kodaira-Spencer map is injective or it's 0. So case 1, let's suppose that it's injective. Then here's my description of the fiber over infinity. It's the image of this closed immersion. So this goes from the moduli space of sheaves on X with Mukai vector C, comma PS, goes to this bigger space, and the map is just E goes to E plus P. And okay, wait, how is this describing the fiber at infinity? Well, by definition, the fiber at infinity, well, okay, I guess it's defined to be the normalization of something. Actually, in this case, the closure is already normal. You don't need to normalize. The fiber at infinity, it's supposed to be some kind of moduli space or a closed subset of a moduli space of Higgs bundles. What's going on here is that all the Higgs fields are 0. So really it's a moduli space of Higgs bundles, but actually it lies inside this, the locus of things with Higgs bundle 0, which I'm just identifying with mx 0 PC p squared s. Okay, so this is the isomorphism that allows you to compare x sub v sub 0 and x sub v infinity. Another way to think about this correspondence between the fiber at 0 and the fiber at infinity is, let's say you take a section of the fiber of the Lagrangian fibration over 0. That section won't deform in this family, but its pth power will deform. So you can deform its pth power over the whole family, and then you can specialize to infinity. And because of how this, because of what's happening with this vibration at infinity, the specialization of this now multi-section to the fiber at infinity is going to give you an actual section of, well, you have this map from the fiber at infinity to PG, and then the Frobenius of PG. And this multi-section will specialize to a section of this upper map. That's geometrically how you get this correspondence. Okay, here's the second case. Let's suppose that the Kodaira-Spencer map is 0. So what's going on here, I think, is kind of intriguing. In this case, this elliptic vibration that you have is the pullback under the Frobenius of P1 of some other vibration.
So is it the same as isotrivial here? Ks is 0 or not? Or it's not about isotriviality?
Yeah, so here, Kodaira-Spencer being 0, it could be isotrivial, or it could be the case that you just factor through the Frobenius, but you're not isotrivial. So for instance, if you take like a semi-stable elliptic vibration on a K3, and you form the Frobenius pullback, you pull back by the Frobenius of P1, and then you take the minimal resolution, that will again be a K3. Its Kodaira-Spencer map will be 0 because you pulled back by the Frobenius, but it won't be isotrivial. Yeah, so yeah, there's sort of, this does not imply you're isotrivial. There's like it's a weaker condition. So you're to pull back like this, and here's what's going on in infinity. I'll just put up the diagram. This normalization map, sort of the normalization is giving you this Frobenius of P1, and in fact, the fiber at infinity is given by pulling back by P1, by the Frobenius of P1, the moduli space of sheaves on Y with an appropriate character. So I guess in sort of slightly broader perspective, the point is that if there's some kind of foliation on X, which is attuned to this Mukai vector V, then the fiber at infinity somehow detects that foliation. So let me close by sort of giving you a sketch or a picture of how you analyze these moduli spaces. So I find this kind of an appealing picture. So let's say D is a smooth curve in this linear system C. Let's consider its pth infinitesimal neighborhood in X. So if D is cut out by an ideal sheaf I, this is the scheme cut out by I to the P. So here's the thing to notice. If L is an invertible sheaf on D, then the Frobenius pullback of L is an invertible sheaf on DP. And if you restrict it to the closed subscheme D, the reduced subscheme, you get L tensor P. Okay, so let me fix a point in PG corresponding to a smooth curve. Sens theorem tells you that any Brouwer class on this curve is 0. And given an invertible sheaf L on D, there's a construction which there's a few details here that are missing, but the output is a family of invertible DTW modules on DP cross A1 over A1, such that on each fiber, if you restrict it to closed, the reduced subscheme D, you just get L to the P. Okay, so, and then you can take the semi-stable limit of this family. So at least, so this is sort of the picture. This gives you a section of P1 TW to X of V. And if you compose this section with F, you just get the constant map T. So this is a section, it's sort of like a horizontal or a vertical slice of this family. Okay, but the point of doing this is to analyze the following question. What is E bar infinity? So what is the, this is, what is the sheaf you get at infinity? That's sort of the key to all of this. So I want to at least give you an idea of how you could answer this. The family, one way to think of it is giving you a morphism to the Picard scheme of DP. Okay, what is the Picard scheme of DP? Well, you can restrict to D, and the kernel is an affine bundle. It's an iterated extension of H1 of OD by itself. If P was 2, then it would just literally be H1 of OD. So in particular, it's an affine scheme. So let me just say L is OD for simplicity. Then our morphism induced by this family lands inside of A. And so, so now there's either two, A is affine is what I'm saying. So either, I mean, and P1 is not affine. So there's either two possibilities. Either this family is just constant, or the fiber at infinity is not an invertible sheaf. And so that's sort of the crux of the matter is analyzing when this family is constant. And this is a question about invertible sheaves on an infinitesimal neighborhood of D. And here the symplectic geometry kind of comes in again in what I think is an interesting way. Somehow the key to what I'm saying is analyzing how if you have a class in a Brouwer class or a class in H2 of X mu P, its splitting on an infinitesimal neighborhood of a curve is very closely related to the behavior of the symplectic form on the infinitesimal neighborhood of a curve, which in turn is closely related to the Kodaira-Spencer map. All right, I'll stop there. Thanks.
Thanks, Dan. Are there questions?
I had a question. So about this theorem where you proved that the fibers are Lagrangian under the assumption that twistor family is not isotrivial or something. Could you go to that theorem, perhaps? Yeah, thank you. So this is actually was reminding me of deformation to normal cones for family of, so usually for that construction, when you deform the Mukai system to the Hitchin system, usually the family is isotrivial and the fibers are Lagrangian fibrations. So this is, do you need this assumption that that it's not isotrivial in order to prove number one?
No, yeah, number one will be true without that assumption. Yeah.
Okay. Okay.
But yeah, I think you bring up a good point. This does seem kind of reminiscent to the deformation of the Mukai system to the Hitchin system. And I think
Right.
I think they're both sort of instances of this, like the Reese construction or one of these filtered things, except in that case, the filtered algebra is sort of it's the completion of the of a curve. It's like the infinitesimal neighborhood of a curve, and that's sort of the filtered algebra that you're deforming.
Yeah.
Here, it's filtered algebra we're thinking about is one of these like Picard algebroid things. But yeah, they have a very similar flavor.
Yeah, that's right. So it will be interesting to know how much can be said.
Yeah.
Yeah.
So I had a question. In that example, when the genus is 1, you gave us sort of an explicit description of the fiber over infinity of that space M.
Mhm.
Is there any kind of description for the higher genus of that space? For the Higgs moduli space, yeah.
Yeah. If you instead make the moduli space on the universal curve, which is a very closely related thing, then yeah, it's essentially the same descriptions as this. Yeah.
Okay. Mm-hmm. And you use that in the proof of the theorem? You need the description of this? Mm-hmm.
Yeah.
Okay. Mm-hmm.
Yeah, I guess maybe this is your how do you prove these things are smooth? I don't actually it would be lovely if there was some like sort of abstract reason why a space with such and such properties was smooth. I don't know of any reason like that. The only way I can prove these things are smooth is just by sort of writing down what they are and then observing that they're smooth. But I think it would be really interesting if there was some sort of general thing at work forcing them to be smooth.
I see. And is that like the obstruction? I guess that's like the obstruction to answering your question in general about the.
Yeah. Yeah. The general case being the higher rank moduli spaces where I don't really know how to say anything. Yeah.
Mm-hmm.
Are there other questions?
Well, I had one other question. What about if you, instead of K3s, because you were saying that like we know representability of this cohomology for any surface. What happens for other surfaces if you do try to do some similar constructions?
Yeah, so I think if you have a surface that's super singular in an appropriate sense, then a lot of similar things should be true. So you can now super singularity should correspond to this this U being positive dimensional, and then you can do a lot of these things. So you can at least go as far as you can make this universal DTW thing. You can take moduli spaces, and then I'd say where the K3 properties come in here is in the analysis of the moduli spaces. So the moduli spaces might not be quite as well behaved for a general surface or something, but a lot of this does work. I think that's sort of the generality these constructions work in is a super singular surface.
Okay, cool.
Are there other questions? So like if you took the surface to be an abelian surface, would you expect to see some similarly nice behavior?
Yeah, I think so.
Right. I mean, because maybe the moduli spaces would be a little easier.
Yeah. That is what I would expect. I haven't actually thought about that case specifically. I mean, I would sort of expect there's a very close there's a one-dimensional space of super singular abelian surfaces. It's basically a P1. I would kind of expect that you could get that P1 by some modular construction like this, but I haven't thought about that.
Yeah. And sorry, in that, maybe you said this, but in that last example that you gave with the the curve on the surface, we should again think of this fiber at infinity as being some kind of P Frobenius image. of the fiber at 0 or whatever? Is that sort of still the picture we should have in mind?
Yeah, the fiber at infinity is, well, yeah, it's I mean, it's, yeah, I guess the picture, it's a little bit, it's slightly indirect. I guess it's maybe the picture is given by this is the correspondence here.
But this picture still, I mean, we should keep this picture in mind in that last example. I see.
Yeah, absolutely. Yeah. This is the this is the picture to look at.
I see. Okay. Last chance for questions. Other questions? If not, let's thank Dan again. And there will be yes, Orange just put it in the chat. There is a Gather Town